do an example where we graph a rational function. Function is 2x squared plus 7x minus 4 over x squared plus x minus 2. And I want to go through a list of things you might want to use when you're trying to graph this. So the first thing is usually what are the zeros or roots. Now, aside from the possibility that some number will turn the denominator into 0, you find the roots by just setting the numerator into 0. So that's 2x squared plus 7x minus 4 equals 0. So we want to factor that. Now we have to see, is that going to factor nice and easily? 2 is 4. No, that's not going to work. 1 and 4. Well, that's 8 minus 1. So, like that. This is reverse FOIL. 8 minus 1 is 7. That's all I really need to know, because I set these up. So the roots are what? 1/2 negative 2. Okay, it's a good start. What is the y-intercept? These are x-intercepts. That's where f of the function is f of 0, if it's defined. Right? It might not be defined, and then you will have an intercept. Okay, so what do we have here? Minus 4 over minus 2 is 2. So now I know where the graph is going to go through the y-axis. What's its end behavior? Well, again, we look at the dominating monomials. That's 2x squared over x squared. The end behavior is this is going to go in both directions to 2. In fact, that answers another question, which is what are the horizontal asymptotes? So it's going to be an asymptote. And finally, what are the vertical asymptotes? Where do we find vertical asymptotes? Places where you have a function kind of going like this, never goes off to infinity. What causes that in the function that we can look at? Well, you should recall it's where the denominator is 0. So again, I want to factor. It's like plus 2 and minus 1, which means vertical asymptotes. X equals 1 and minus 2. All right, so we've gathered our information. Now we're going to strike out and see if we can get an idea what this function looks like when we graph it. So at (1/2) and negative 2 is going to go through the axis. The y-intercept is 2. So we can already see, well, we're not sure yet. let's look at the vertical asymptotes at 1. And at -2. Really? No, -4. Sorry. No. The zeros, I'm sorry, I got the zeros wrong. The 0 should be -4. And we have an asymptote here. Well, it would be nice to know what is the function doing as it gets close to these asymptotes. So we might want to just pick a number, or we might want to just take a look. Over here, it's say 1.5. 1.5, what happens? Well, and it'd be nice to have a calculator handy, but 2 times 3/2 squared plus 7 times 3/2. I'm just trying to get the sign of this. Because if I have the sign, it's either going to be going up or down. It's negative, it's going to be going down. 3/2 squared plus 3/2 minus 2. So we have 9/4 plus 6/4 is 15/4. Well, that's a lot more than 2, so this is greater than 0. And what do we have here? Well, it's already obviously greater than 0. So we know that as we head into this, it's going to be going up. Well, now's a good time to introduce the fact that there's an asymptote of 2. So this is probably going to be going this way, right? Right. We can see already that this asymptote is going to be going down. This is going to go through 2. And it's going to pass through. It's going to go through 1/2. It's going to pass through 2. And what else is it going to do? Well, over here, at -4, what happens at -5? I think pretty obvious it's going to have to go here. Well, I'm just guessing. We're going to have to take a look. We're going to have to. Oh, there's an asymptote here. Oh. So it's probably one like this. There we go. I have to use all this information to carry this out. Now that's kind of a good guess. I can tighten this up by picking some points, like 1, 2, -3 would be a good point to see where this actually is. I don't know, somewhere in here might be useful. Let's just see how good my intuition was. You can't really tell. Is that what I drew? Or did I get it wrong? well, this is a little smoother. And did it come up? Did I not check this? Right? Huh. Got that right? I got that right. No, this is the problem over here. It's coming up from over here. Why did I decide the wrong thing here? Oh, I guess I didn't check coming in from this side. I think that was it. So that's more or less what it's actually like. All right, well that's kind of the idea. Rational functions are the most difficult things. Fortunately, I mean, again, let's take a look at this. We've got an asymptote here, here. I guess actually a little smoother. We've got an asymptote here and here, and we've got zeros here and here, and y-intercept at 2. So there's kind of a whole kind of story behind it. Again, I'm not sure how crucial this is. I think understanding how these things fit together is important, but actually getting the graph exactly right isn't as important today, since we have technology that can check it for us. Just as we used to emphasize adding and multiplying and getting it exactly right, we have calculators. All right, any other questions about this? Because we're going to move, this is the last bit of information that might be on the exam. We're going to move on to a new subject. Yes?
Why is it that the line in the middle crosses the y-axis?
Well, how do we know that?
Yeah.
We plug in 0. That gives us the x-intercept. So if I plug in 0 here, I get -4 over -2 or 2. That's always useful. I mean, you can argue any point I pick on here might be useful. The y-intercept is usually pretty easy to calculate because we're just plugging in 0 for all your x's. All right. I'm going to take a few deep breaths for a minute. Then I'm going to ask you a job application quiz. Now, this might not apply, this might not go to heart for some of you as much as many as others, but I do know that there's a fair number of computer science majors here. So here we go. In the future, you're interviewing at some giant corporation. It's the Apple, Google, Facebook Corporation. They've all merged. This is a great place to work. Great benefits, really high salaries. All you need to do to get hired is to take a quiz, a little quiz. To show how good you are at math. They give you 2 choices for your quiz, for your salary. Choice 1 and choice 2. Choice 1, you start 1 penny a day the first day, and then the next day it's 2 pennies, and then it doubles for the first month. And then whatever it's at the end of the first month, that's your salary for then on per month. Or you can get $1 million a month. Which do you want? Oh, well. Who wants number 1? Okay, 1, 2, 3, 4, 5, 6, 7, can't really see, 8, see 8 people. Not everybody's going to vote. Who wants the $1 million? Now, keep in mind, if you only make it through the first week, that's probably was the best. Yeah, 1, anybody else? 2, 3, 4, 5, yeah. Okay, that's good enough. It's not, doesn't seem real obvious, does it? Do you have a calculator here? Could you type in the following? Can you type in 2 to the 30? I didn't mention you have to work 7 days a week at these companies. Yeah. Tell me what number you get.
107,374.
Just slowly.
Sorry.
1073
7,
7.
4,
Yeah. What happens after
1,
1,
8,
8,
2,
2.
4. That's it.
That's pretty good. $10 million. You thought number choice is number 2, and they're not going to hire you. That's pretty good. What's the point of this? This here we're talking about an exponential function. This is going to be section 4-1, and maybe we'll get on to 4-2. Exponential functions. 2 to some big number. Can be a big number. So, definition of an exponential function is a function a raised to the power of x, where a is greater than 0, and a is not equal to 1. If a is greater than 0, this is an increasing function. Let's take a look. Well, we saw that. It's 2 to the x, right? As x gets bigger, 2, 4, 8, right? If a is less than 0, it's a decreasing function. We say 1/2 to the x. 1/2, 1/4, 1/8. It's good to note that if a is less than 0, okay, that's not what I wanted to say. I guess what I wanted to say is, if you have 1 over a to the x, that's just a to the minus x. So just by switching the signs here, you know, we can make a 1 over a, would make it a is greater than 0, then 1 over a is less than 0, and vice versa. Just by switching the sign here, we can go back and forth between an increasing and decreasing function. All right, just going to make one more remark before we take a break. There's something kind of insidious about exponential functions. If you have a polynomial function that's increasing, and an exponential function that's increasing, there's always going to be some x where for all, well, I'll just say, I guess I'm going to say m, where if x is greater than m, the exponential function is greater than the polynomial function. Now, I just made a really broad statement, but let me give you an example that's really, it's kind of shocking. Let's say e to the x is 1.00000. Doesn't really matter. Just put a 1 at the end of it. That's greater than 0, right? Greater than 1. So this is an increasing function. Think about that function. Think about putting 2, 4, 8, 1,000. It's growing very slowly. Now I'm going to have a polynomial function, x to the, oh, we'll just put in 1 billion. Think about how fast this is going. Put in a 2 here, zoom, I'm off the chart. But this function, eventually, there's some m, where if we get out to m, from then on, this function is always going to be greater. Exponential functions are, they're relentless. They overtake every single polynomial function. You put in more zeros here, it doesn't matter. You put in more zeros here, it doesn't matter. Okay, I'm going to take a break for a few minutes, and then we'll get exponential function. What an exponential function looks like. Let's graph one, just using some points. Let's graph f of x equals 2 to the x. So 2 to the 0, that's just going to be 1. It's going to pass through 1, it's y-intercept. At 1, it's going to be 2. At 2, it's going to be 4. 3 is going to be 8. Negative 1 is going to be a half. Negative 2 is going to be a quarter. It's going to look like this. Its end behavior to the right is it's just going to get larger and larger. Its end behavior to the left is it's going to approach 0 asymptotically. Now let's compare that with a slightly different function, f of x. What if we just change what we call the base? Okay. Still goes through this, the axis at the same place. 1 is now 4. 2 is now 16. Negative 1 is now a quarter. And what's happened? The base got larger. The rate at which it goes up is much faster. The rate at which it comes down is much slower. However, the shape, except for scale, is basically the same. This is for a greater than 0, increasing. And you're actually going to find that's true for all exponential functions. They're all basically the same shape. What happens if I take my f of x and I want to say 4 of that, 4 to the x. What happens if I just multiply it by some number? I say did want to use 2 to the x. I'm going to create some new function, h of x is 2 times f of x. 2 times 2 to the x. Well, let's 2 to the x plus 1. Oh. Now, if you recall, we talked about transformations. Anyone recall what changing x to x plus 1 does to the graph? I guess we should see. Let's graph this new function. So at minus 1, we have 2 to the 0. It goes through 1. 0 is 2. 1, that's 2 to the 2, it's 4 now. And likewise, minus 2 now is 1/2. So what have we done here? All we've done is we've shifted it minus 1. That's what changing x to x plus 1 does to any function. So it's just a transformation. All right, now I mentioned functions where a is less than 1. So let's take a look at one of those. Let's just look at f of x equals 2 to the minus x. I'm sorry. That's not right. Want a less than 1, that would be 1/2 to the x. All right, so at 1, it's 1/2. 2, it's 1/4. 0, it's 1 again. Minus 1, well, it just becomes what? It's 1/2 to the minus 1. I'm trying to be thinking through what I'm saying. 1/2 to the minus 1. That's just 2 over 1 to the 1. That's the law of exponents. It's just 2. So it's 2, 4. It's just a mirrored reflection here. And you can see that because negative 1/2 to the x is just 2 to the minus x. We think about this kind of transformation. If you change x to minus x in a function, it's just going to be a reflection over the y-axis. So that's what happens with a less than 0, less than 1. Okay. One more transformation we should look at is, well, what happens if I have f of x equals minus 2 to the x? Well, I'm just going to draw in, this is 2 to the x. What happens here? Yes?
It gets mirrored over the x-axis?
It just gets mirrored over the x-axis, right? But otherwise, it's the same kind of function, same shape. All right, so those are some basic things about exponential functions. Now, let's actually have a real-life example that I had to deal with a few years ago. Any biologists here? Nuclear physicists? Any nuclear physicists? No, not yet. Nope. We're going to learn some nuclear physics here. In general, if you have a radioactive substance, we'll call it I of X, because we're going to talk about iodine. The amount of radioactivity is some number to the X, where A is less than 0. In other words, it's an exponentially decreasing function. Now, what does this have to do with? Well, there's a condition that some people get called hyperthyroid. The thyroid starts working overtime. It regulates various things in your body, and it's not good. We call it Graves condition. Anyway, a lot of cats get this when they get older. I've had a lot of cats. I've had 3 cats who had this condition. And it's a benign tumor, and it grows, and stops eating, and, without doing something, it would perish. So the treatment seems kind of unusual. Here, terrible drawing of a cat, but it's a happy cat. Like us, it's got a thyroid. And we inject in the cat radioactive iodine. I'm just going to do a little asterisk. Why iodine? Well, iodine accumulates in your thyroid. Your body just filters it out and brings it to your thyroid. But because it's radioactive, it gets in there and starts killing off the thyroid. And if you put exactly the right amount in, it kills off exactly the right amount of thyroid, saves the cat's life. This is actually, if you're a nuclear physicist, this is iodine 131, that's its molecular weight. If you're a chemist, you might know what that is. Okay, so that was the treatment. You send the cat off to the vet, stays there for a week or a month, it's giving off radiation, which could give you cancer. And then the cat comes back, and they tell you, there's still radiation coming out of this cat, so you can't throw the cat litter into the garbage because it's radioactive. You're not allowed to throw radioactive waste into your garbage. So that was a real problem I had. We had this cat, and I had to figure out, how do I deal with this? So here's the equation. The amount of radioactive iodine by day, we start at day 0, is equal to the starting amount times 1/2. This is what's called a half-life. Radioactive substances have a half-life of D over 8.02. So the half-life is 8.02 days. Every day there's half the amount. I'm trying to make this real here. So the question I had was, well, how long do I have to wait until I'm pretty sure that the garbage people won't detect this radiation and come and, someone's going to come knocking at my door with a warrant. So what I want is this amount to be a millionth of what we started with. I figured, they won't be able to detect that. So let's divide both sides by I0. And I get that this ratio, again, I'm starting here, and somewhere down here, we're at 1/1,000,000. I want to know where that is, how many days that is. So, I sub d over by 0 is the starting amount, so this is the ratio. I want that to be a million. And that's 1/2 d to the 8.02. Really what I want to know is the number of days. All right, so how do I figure that out? Well, one way, sorry, cat, is to just kind of draw a chart. We have days. Now we have P over T, I. Right, so just start plugging things into a calculator. After 10 days, we've got 0.42 left. 100 days, 0.00018 left. 150 days, 0.00050 zeros. 3. And closing in 160 days, approximately 0.00001, which is 1 million. So I had to put the kitty litter in a garbage pail in my backyard for 160 days, or about 5 months. Now there are other ways to solve this that we'll run into and get an exact number, but I didn't need to know the exact number. I don't know what they do with, when people have this treatment, I guess they let them go after a few days. And then, maybe you want to keep your distance from them. All right. Just some more interesting things to talk about exponential functions. If I take an exponential function, and I take a point on the exponential function, and then another point near that point, well, I can draw a line through it, right? And that line would have a slope. And I could graph that point, that slope. Let's call this x and f of x. Call this x and slope. So if I take another point on here, a little further away, and another point nearby, I'm also going to get a slope. That's going to be it's going to be greater. If I take a point down here, you can see it's going to be closer to 0. If I keep doing this, I get this kind of wonderful result. So if I graph the slopes along here, the approximate slopes, what I get is another exponential function. This is something you will, no doubt, when you take calculus, you'll investigate further, but all by itself, it's just it's a really fascinating kind of feature of these functions. I could repeat this, right? I have an exponential function, I could get the slopes here, I could get another, and another. All right. So let's say you have some exponential function, and you want to evaluate it at some points. So f of x equals 2dx. And let's say we pick some weird rational value, 123 over 454, just a made up number. So you think about that, so f of 123 over 454 is 2 to the 123 over 454. And you look at that number and you go, well, I have a calculator, but what does that mean? Well, fortunately, we've talked about this. What that means is this is 2, the 454th root, and either inside or outside, we're going to raise it to 123. This is just from the laws of exponents. Might be hard to evaluate it, but at least we know what it means. What if I'm evaluating points and I want to evaluate f at the square root of 2? That's a little harder to kind of get your head around. Or how about 2 to the pi? These are irrational numbers. There's no rational expression. We can't do this. So what do we do? Well, let's take an example. Say we're going to take x equals square root of 3. So the square root of 3 is approximately 1.73250, but of course it goes on. So I could start by evaluating 1.7. And then 2 to the 1.7. Well, that's a rational number, so I know how to handle that. That's approximately 3.2490. And I could try a better estimate. And I get 3.3173. Again, not exact. 732. I'm going to get 3.3219. 732. I'm just adding numbers here. 3.3219. Okay, I don't really know what comes after that. And finally, 1.73205, this will be my last estimate. It's approximately 3.3220. So you see what's happening here is, as I use more and more decimal points, I'm getting closer and closer to some number. Now that should remind you of something. If I'm trying to evaluate the square root of 2, I can start writing it out, 1.7322005. As I get more and more numbers here, I get closer and closer to a number that's square root of 2. In the same way, that's how I evaluate the exponential function at irrational values. We would say that x to the square root of 3 approaches some limit. There's some number out there that it approaches closer and closer, and that number is called that the limit. And that's what we use as its value. about this idea? Now here's an example that all of you will run into. If you're a business major, this is going to be right up your alley. This idea of using an exponential function to handle compounded interest. Does everyone know what I mean by compounding interest? You put money in the bank, they say, they give you some interest rate, 2%, 5%. And then after they give you your 5%, the next period, you get that much more money in the account, but you get whatever that interest rate is for your new amount, and it grows and grows and grows. So let's say we have an account and it gets 5% interest. That's yearly interest. And let's say they compound it every month. So every month they take what we call your principal, and they multiply it by 1 plus 5%, 0.05 times divided by 12, because it's 12 months in a year. So after a month, instead of P, you've got P times 1 plus 0.05, 12. Well, that's after the first month. After the second month, you multiply whatever you had times 0.05, 12, 1 plus 0.05 over 12, and so forth. So we can write this as P to the number of months you put your money away at. We're going to use P0 as your original amount times 1 plus 0.05 is 12 and M. Well, that should look familiar now to what we've been doing. This is an exponential function, isn't it? If you think back about the first example I gave showing that exponential functions get very large very quickly, that should tell you that this could be a good deal. If you put away a little bit of money today, when you retire in 40 years, it might be a lot more money. Right? That's just good finance. Now, there's a question here. You put your money away in a bank account and they quote you, they'll almost always quote you with yearly and effective yearly interest. But they might compound it at different rates. They might say, well, you got to put your money in for a year, and then after a year we give you your 5%. So you start with $100. At the end of the first year, you've got 105, and so forth. Or, as in this example, they might compound it every month. Right? If you go in after 6 months, well, you don't have 105, but you have more than half that. So let's just take a look for a second at how that works. We're going to start with $1,000. This is our P of X equals P0. And we're going to compound it yearly. This number tells you how often we're compounding it. Well, but we're going to compound it for 10 years. So 1 times 10. And what do we get? We get 16, 28, 89. You can put this in your calculator and check if you wish. That's P of 10 years. 1 plus interest over compounding. Use CY. I don't think those are the right letters, but I'll use those for now. Well, what happens if I'm instead compounding every month? So now I have to get 10 years worth, I have to multiply this by 12. And again, if you use your calculator, it comes out a little better. We need $20 more. I'm going to go one more step. Let's say you have a really nice bank, and they're going to compound it every day. Okay, so again, we start with $1,000. We multiply it by 1, it's 0.05, divided by 365, and then we raise it to this power of 365 times 10 for 10 years. And we do a little better, but not much. Going from yearly to monthly, we made another almost $20. Now we just make it $1. So there's diminishing returns here. Okay, so I'm going to put in the right letters that business people use. P of T is your principal, 1 plus R, your interest rate, over N to the R, to the NT. That's the official formula one should use. Now, there's a little more here when it comes to exponential functions that's really important. Really important when you get to calculus. And it really has nothing to do with compounding. That's the context we're going to look at. So I'm going to ignore the R for the moment and the T, and I'm just going to write this expression. And I'm going to look at what happens to this expression as n gets bigger. Just curious, has anyone seen this before? Anyone recall this, where we're going? Okay. Most of you might have seen this before, but I guess not. So if I plug in 1, well, that's 1 plus 1 over 1 to the 1 is 2. If I plug in 10, well, you need a calculator, but it's about 2.59. This goes 2.745. 1,000, 2.7169. 10,000, 2.7184. It's starting to look like it's settling down. We're stuck on a 7 here. Now we've got a 1. So one more, go 100,000. And we get 2.71828. And then here, some more numbers. If I keep going, these numbers aren't going to change anyway. We settle down to The other numbers will keep settling. We're approaching a limit. That's a weird looking number. Anybody recognize this number? Okay, this is one of the most important numbers in mathematics. It really has a lot to do with things other than compound interest. So important that it gets its own letter, E, and this is called Euler's constant. Euler, very important, brilliant mathematician. Anybody have your calculator with you today? Take a look on there, and there's a button. E to the x. Right? It's important enough it's on your calculator, and most of you didn't even know why it was there. Well, what does this have to do with compounding interest? If I go to a bank, and instead of saying we compound it yearly, monthly, daily, we compound it every instant, every infinitesimal instant. Instead of this equation, we get a very much simpler equation. Our original amount times e to the RT. Many banks actually do this, although when you go in to get your money, they don't have a stopwatch and say, now, here's how much you get. Do an approximation. But they're using this formula to calculate how much they owe you. It's called continuous interest or continuous compound interest. If you're involved in business, this is very important because this is typically how loans appreciate and how interest appreciates. All right, I think that's exponential functions. There's going to be some homework. You don't have to focus that hard on homework. You can focus on getting ready for the exam. I think everybody already knows I put up a sheet of this is things you need to know for the exam, and I put some example kind of questions so you can do that. And you can bring stuff in on Thursday if you have some questions about it. All right, I think we're done. Yes. Yes. You get to use a calculator, TI calculator, not a phone, and you get one double-sided sheet of paper. Last point, I sent this out as an announcement. I will not be here for the exam. A colleague of mine, I'm going to be out of the country, but he's very knowledgeable.